Hello friends, welcome to the video lecture series on digital image processing. I am Professor Dafda, and in this 66th video lecture of DIP, we will study polygonal or boundary approximations using minimum perimeter polygons or MPP in representation for digital image processing and its implementation in MATLAB. We are learning different image representation techniques, and minimum perimeter polygon is one such technique. So starting with the name, what is the meaning of minimum perimeter polygon? As the name suggests, it will give us a polygon that is having minimum perimeter. That means minimum boundary for any shape, and if it is minimum, then it will be computationally more efficient and fast. So polygonal approximation is an image representation approach in which a digital boundary can be approximated with arbitrary accuracy by a polygon. For a closed curve, the approximation is exact when the number of segments in polygon is equal to the number of points in the boundary, so that each pair of adjacent points defines a segment in the polygon. So this polygon approximation using minimum perimeter polygon is a technique used in digital image processing to simplify the representation of shapes or boundaries while preserving their important features. Let us say, for example, you have a drawing of a complicated shape like a curvy coastline or a bumpy road on a map. So instead of using every tiny detail of the shape, you want to create a simpler version that still captures the overall shape accuracy, and that is done by MPP. And what is the aim of this MPP? The aim of this MPP is to capture the essence of the boundary shape, the fewest possible polygonal segments. Okay, and along with polygonal approximation using MPP, we will also understand polygonal approximation using merging technique and splitting technique. So let us start. See, in image processing, these are the main steps. We acquire an image, we do the pre-processing or enhancement, we do image segmentation, and then we do representation and description, which we are learning currently. And after representation and description is done, we can do image classification or interpretation or some object recognition from the image that will give us the result. Image representation is used to convert the raw output that is obtained from image segmentation into another format suitable for processing the image. Different image representation techniques can be chain codes, polygonal approximations, signature, boundary segments, and skeletons. Chain codes we have already learned in the previous video class. In this video class, we are learning polygonal approximation, which further is of three types: minimum perimeter polygon or MPP, polygons using merging techniques, and polygons using splitting techniques. MPP captures the essence of the boundary shape with the fewest possible polygonal segments, while the merging technique is based on average error. Here we merge the points along a boundary until the least square error line fit of the point is merged. But the disadvantage over here is that the vertices do not always correspond to the inflections in the original boundary. While polygon approximation using splitting technique is more advantageous as compared to merging technique, and this technique is used to subdivide a segment successfully into two parts until a specified criteria is satisfied, and this technique has the advantage in finding prominent inflection points. Let us understand minimum perimeter polygon or MPP in detail. Say we have an object boundary like this. In this B image, a grid is superimposed on this boundary. In this B figure, we are finding a group of cells that enclose this boundary completely, which is shown using this gray cells. Now this boundary will have two walls, the inside wall and the outside wall. This is the inside wall and this is the outside wall. Now think this black object boundary as a rubber band which is contained inside this outside and inside wall. Now if we allow this rubber band to shrink, then the rubber band will be constrained by the inner wall and the outside wall, and it will form a polygon of minimum perimeter that fits the geometry established by the cell. So we can see here that here we have reduced the area inside the original boundary to a smaller area inside the MPP. Now this reduced area inside the inside boundary is shown with dark gray shade in this figure. Now we will traverse this dark gray region boundary in the counterclockwise or anti-clockwise direction like this, and we will obtain the convex vertices or convex corners, which are shown with white circle, and the concave vertex or concave corner, which is shown with a black circle. So convex vertex is one where the angle is less than 180 degree, you can see here, while the concave vertex is one where the angle is more than 180 degree, like this. Now for this every black dot, you can find a point that is diagonally opposite on the outer boundary like this. So this point has this point as diagonally opposite. Similarly, this point, we have to only consider the black points, right? This point, Now the minimum perimeter polygon will be formed joining these white dots and the diagonally opposite black dots, which is shown over here. And in computer, this can be done using a specific minimum perimeter polygon algorithm. Let us understand the algorithm. For the MPP algorithm, the convex vertex is represented the symbol W, which is for a white circle, and the concave vertex is represented by a symbol B, which is for the black circle. Then the MPP algorithm says that number 1, the MPP bounded by a simply connected cellular complex is not self-intersecting. So this MPP boundary which will be formed will not be self-intersecting. Number 2, every convex vertex of the MPP is a W vertex, but not every W vertex of a boundary is a vertex of the MPP. This is our MPP and convex vertex is white circle. So every white circle is a white vertex, but not every white vertex is a part of MPP. You can see this is not a part of MPP. Every mirrored concave vertex of the MPP is a black vertex, but not every black vertex of a boundary is a vertex of the MPP. So every concave vertex is a black vertex, but not every black vertex is a vertex of the MPP. So we can see these two are not part of the MPP. Next is all B vertices are on or outside the MPP and all W vertices are on or inside the MPP. So all black vertices are on the MPP or outside the MPP. We can see here. While all the W vertices are either on the MPP or inside the MPP, as we can see this one, right? And next and last is the uppermost leftmost vertex in a sequence of vertices contained in a cellular complex is always a W vertex of the MPP. So this is the uppermost leftmost vertex, which is a W vertex. Say for example, this is our binary image and this is the 8 connected boundary of this binary image. Now we want to find the MPP for this boundary. So figure C, D, E, F, G, H and I are the MPPs that are obtained using square cells of sizes 2, 3, 4, 6, 8, 16 and 32. And here the vertices were joined by a straight line for display. And the number of boundary points that is used in this figure is 1900 and it goes on decreasing from 1900 to 206 boundary points, 160 boundary points, 127 boundary points, 92 boundary points, 66 boundary points, 32 boundary points and 13 boundary points. And we can see here that as we go on decreasing the boundary points, the polygon becomes smaller. So this figure E, which has 127 vertices, retained all the major features of the original boundary while still achieving a data reduction of over 90%. So here we see a significant advantage of MPPs for representing a boundary. And also further we see that MPPs perform boundary smoothing. So approximating using less number of boundary points will give us minimum perimeter polygon. Okay, so this figure minimum perimeter polygon we will be also implementing in MATLAB at the end of the class. Let's go ahead. And these are the advantages of MPP approximations. It helps strike a balance between accurately representing a shape and simplifying it for practical purposes. It's like creating a simpler version of a complex shape by connecting a few key points with the shortest line possible while still keeping the main characteristics of the shape intact. And it is used in various fields of image processing, computer graphics and geographic information systems. The next technique for polygonal approximation is merging technique. Here we merge the points around the boundary and fit a least square error line to the points until an preset threshold is exceeded. So if this is our start node, we merge the points E1 plus E2, which is less than threshold, and we also check E3 plus E4 plus E5, which is greater than threshold. So we will not consider this point as the vertex, and rather E1 plus E2, which is less than threshold, will be considered as the vertex. And similarly, we will proceed further, and once the start point is reached, we will intersect all the lines. So this is a good technique, but the disadvantage over here is that the vertices do not always correspond to the inflections or actual corners, and therefore MPP is more useful. While one more technique is the splitting technique of polygonal approximation. Say this is our object boundary. We find the line joining the two extreme points Here the two extreme points are A and B. And after that, we find the farthest perpendicular point from this line, which is C and D over here. So now we compare this distance of C and D to the threshold which we have chosen. Say the threshold which we have chosen is half of this complete AB line. So if this point C is greater than threshold, then this will become a vertex like this, as well as this D. If it is greater than threshold, that is, if the distance exceeds the threshold, the point will become a vertex. And then we again subdivide the segment into two segments which we obtain, and again we check it with the threshold, and this is repeated until the initial point is reached, and hence we find the polygon like this. And this technique is advantageous as compared to the merging technique. Here the advantage is in finding the prominent inflection points, but still the more advantageous technique is MPP for polygonal approximation. Let us implement MPP in MATLAB. So that is all for this video class. Thank you very much.